This Cauchy-Euler equation will be for the imaginary root case. So here we have Cauchy-Euler equation, x squared y double prime plus 3xy prime plus 2y equals 0. So again, we're going to guess y equals x to the r. We're going to try and figure out r in order to make that solution work. And then, we need the derivative, so y prime equals r times x to the r minus 1. And y double prime equals r times r minus 1 times x to the r minus 2. Next step is we plug those guesses into the differential equation. So we have x squared times r minus 1 times x to the r minus 2, So that's the x squared y double prime term, and we have plus 3x times the y prime term, which was r times x to the r minus 1. And we have our y terms, that's just 2 times x to the r, and that all equals 0. So next step is we're going to simplify this. So we have our x squared, x to the r minus 2. We have x times x to the r minus 1, and then x to the r. Those all end up being x to the r in each term. So we end up with r times r minus 1 times x to the r. Then we have plus 3r times x to the r plus 2 times x to the r equals 0. So next up, I'm going to factor out the x to the r. I'm also going to expand that. So this is r squared minus r plus 3r plus 2 times x to the r equals 0. So our only possibility for all values of x to get this whole expression to equal 0 is to have this polynomial equal 0 for a particular value of r. And so now we get to solve for that. So it's r squared. I have my minus r and my minus 3r, so that's plus 2r. And I have a plus 2 equals 0. And I don't see how to factor this off the top of my head, especially it's going to end up being complex, so it's hard to do in your head. So let's just use the quadratic formula. So r is equal to, so we have negative b, so that's this term here, so we're going to have negative 2 plus or minus the square root of b squared, so here I'll put 2 squared, minus 4 times a, which is 1, times c, which is 2. All right, and that's all over 2 times a, which is 1. All right, so now let's go ahead and try and simplify that. So that's negative 2 plus or minus square root. Let's see, that's 4 minus 8 over 2. All right, so then r is equal to negative 2 plus or minus square root of negative 4 all over 2. That can simplify further into negative 2 plus or minus, so it's negative 4, and then the square root of 4 is 2, so it's going to end up being plus or minus 2i, and that's all over 2. So out of here you can get negative 1 plus or minus I. All right, so then the solution in those cases, this is alpha plus beta I is equal to negative 1 plus or minus, it's 1 times I. So the alpha in this case is negative 1, and the beta is just 1. And the solutions will end up being, in this complex root case, you get x to the alpha times cosine of beta times the natural log of x. And the second solution, y2, is equal to x to the alpha times sine of beta times the natural log of x. All right, which is a whole lot simpler than if we had just done two complex powers. So if we plug it in now with our numbers, this is x to the negative 1 times cosine. Beta is just 1, so it's just cosine of the natural log of x. Then y2 is x to the negative 1 sine of 1 beta times the natural log of x. Yeah, those two solutions, it would be a little horrible to plug in, especially the second derivative. You get a lot of terms. But these two will satisfy this Cauchy-Euler differential equation. You could have also plugged in y1 is equal to x to the negative 1 plus I. And you could have also plugged in, y2 equals x to the negative 1 minus I. Those should also work, it's just they're imaginary, and it turns out that if you want to convert from these to here, they end up being equivalent solutions.